Welcome to Linear Algebra for Data Science. This course will cover key concepts and applications of linear algebra for data science. You will learn about the vectors, matrices, and their role in data representation. You will also learn linear transformation, eigenvalues, and eigenvectors, and how these concepts are applied in data science, especially in statistical analysis and machine learning. Now, let's get started. First, let me introduce what linear algebra is and why it is important. Linear algebra is a branch of mathematics that deals with vectors, vector spaces, linear transformation, and more. Linear algebra studies how lines and surfaces interact, move, and transform in space. Linear algebra is widely applied to the practice of data science. Learning linear algebra will give you a deeper understanding of many concepts in data science. The beginning of linear algebra dates back over 4,000 years to ancient Babylonia. They developed a method for solving the linear equations that underlie linear algebra. In the 200s before Christ, Chinese mathematicians invented the first version of Gaussian elimination. They used this method to solve systems of linear equations and significantly advanced their studies. Gaussian elimination is still one of the main methods used in linear algebra today. Another important concept in linear algebra, vector, was invented in the 19th century. The discovery of the vector contributed to the remarkable development of engineering and physics during this period. One of the central ideas of linear algebra, the study of vector spaces, took place in the early 20th century. And with the advent of computers in the middle of the 20th century, the application of linear algebra to practice has grown exponentially. Vectors and vector spaces are central concepts in linear algebra. What are they, by the way? Let's start with the vectors. Vectors are like arrows pointing into space, characterized by direction and length. Vectors can represent various physical quantities with magnitude and direction, such as forces and velocities. In data science, vectors often represent data points in a data space, with each element of the vector corresponding to a different feature of the data. Now, let's discuss vector spaces. A vector space is a collection of vectors that follow specific rules. These rules include vector addition and scalar multiplication. Spaces in linear algebra are not limited to the three-dimensional world in which we live, but can have any dimensions beyond 4. Vectors and vector spaces are the concepts relating to operations such as transformation and reductions performed in linear algebra. They are also the framework for manipulating and interpreting data in data science. Next, let me introduce some key concepts other than vectors, matrices, and linear transformations. First, let's discuss the vectors a little more. Put simply, a vector is an ordered list of numbers. These numbers can represent anything from spatial coordinates to variables in equations. Geometrically, we can regard a vector as an arrow pointing in a particular direction, length, or magnitude. For example, consider the vector 3, 4. In two-dimensional space, this vector represents a point 3 units along the x-axis and 4 units along the y-axis. We can visualize this vector as an arrow starting at the origin 0, 0, and ending at the point 3, 4. Next, let's discuss matrices. A matrix is a rectangular array of numbers arranged in rows and columns. Each number in a matrix is called an element. For example, consider the matrix on this slide. It has 2 rows and 2 columns, so it is a 2 by 2 matrix. The number in row 1 and column 1 reads 4. The number in row 1 and column 2 reads 3, and so on. A matrix can represent more than one vector at a time, or a space transformation. Finally, let's talk about linear transformations. A linear transformation is a rule that takes one vector as input and produces another vector as output, while preserving the structure of the vector space. In other words, it's a way to transform one vector into another while keeping specific properties intact. Suppose we have vector 2, 3 representing points on a two-dimensional plane. A linear transformation that doubles the x-coordinate and leaves the y-coordinate unchanged gives the vector 4, 3. This is because 2 by 2 equals 4, and 3 by 1 equals 3. Vectors, matrices, and linear transformations open up new possibilities for data science applications, and understanding them will deepen your understanding of data science. These concepts interact in various ways. For now, having a rough idea of these concepts is sufficient. Subsequent lectures will explore each of these concepts in greater detail. Thank you for watching. Please thumbs up and subscribe to my channel.